Good evening, everybody. Welcome to the Doctoral College Inaugural Lectures. This is what, the second one this year, or the third? There's so many, they're so interesting that we all merge together. My name's Dave, I'm the Dean of the Doctoral College. This evening we've got 3 speakers for you. We usually only have 2, but I think there was a little bit of a bun fight about timing, so we decided to do 3. We'll still run it over an hour. We're going to speak for 15-ish, give or take, something like that, and then there'll be an opportunity for some questions at the end. I always say this, and I always mean it, that these are really, the highlight of the year for us. These are activities that were awarded last year. These really are the best of the best of the best of the PhDs that we award in the University of Leicester. They're incredibly competitive to even get nominated for these, and then to actually make it to give the Doctoral Lectures is an incredibly prestigious thing to do. And we've had some absolutely corking speakers over the last years, and I think this evening won't be a disappointment to you. So enough of me prattling on. We're going to kick off proceedings with Joe Emmings. So I'm going to assume that your first slide is probably going to be to introduce yourself, so we'll let you do that yourself. It's probably the easiest thing to do. So Joe's going to talk about from, his title's up there, I'm not going to read it. So Joe, we're not doing all the lecture.
Good evening, can everyone hear me okay? Yeah. So it's a real honour to have been invited to give this doctoral inaugural lecture, and it's a real privilege to be able to subject you to 15 minutes of looking at and talking about mudstones of all things. So firstly, I must acknowledge a long list of supervisors and co-workers who have contributed towards this research. So I'd firstly like to see a show of hands. Who has a fairly good idea of what they believe to be a good definition of a black shale? Who thinks they know what a black shale is? 2 hands. The 2 supervisors. 3. Okay. Yeah. Good. All right. So a black shale is an organic rich mudstone. Okay, and mudstones account for over half of all sedimentary rocks, and around 2/3 of the rocks exposed at the Earth's surface are sedimentary. So mudstones already, because they're so abundant, are quite important for a variety of applications. We're interested in a UK black shale, specifically the Bowline Shale. One of the reasons is that it's one of the thickest black shale successions in the world. They're important for a variety of reasons, right? The Bowline Shale, you probably think of shale and probably one thing comes to mind, and that's shale gas and fracking. So it's sort of undoubtable that black shales play a really important role in oil and gas, so in hydrocarbon source and reservoir rocks. But I think it's really important to stress too that mudstones are important for a variety of other reasons, primarily because they tend to exhibit low permeability. So they make very good seals for the storage of carbon dioxide. So as part of carbon capture and storage technology, mudstones play a really important role for things perhaps like compressed air storage and also geological storage underground of things like radioactive waste. Did you know also that black shales can be really quite enriched in metals? So in some cases we actually mine and can mine black shales for things like vanadium. So here we have a plot of the concentration of vanadium in the UK Bowline Shale compared to a typical black shale and what we define as a highly metalliferous shale which might be mined. Vanadium is of particular interest because it's a critical metal, so it's used in renewable technologies, battery technologies. So we'd like to know why. Why is there so much vanadium in the Bowline Shale? And lastly but not least, they provide really a window into some really exceptional processes that occurred on the Earth. So what does a typical black shale look like? So this is an example from an outcrop in Lancashire where I spent some of my work during my PhD. If we zoom in and were to take a sort of a virtual sample from this location here and take a piece of mudstone and cut it into a cross section, this is what it would look like. So there's not much going on, right? And really that's unfortunate because I think mudstones have definitely gained a reputation within the sort of world of geology as being rather boring and mundane rocks. But we're looking at the wrong scale. Okay, so if we were to zoom in a bit closer, so now we're looking at the scale of micrometers rather than millimeters using an electron microscope. Actually, it's quite clear there's a really diverse array of textures present in these mudstones. And for the purpose of this talk, these bright spots, these are really important. So this is a high density mineral. This is pyrite or fool's gold. So actually, many black shales contain quite a lot of pyrite. And that's really quite important when we think about the environment of deposition and sort of the chemical reactions that were going on during burial of these rocks. So heterogeneity, it's important. So microscale heterogeneity in something like the Bowline Shale undoubtedly has an impact for upscaling, thinking about geotechnical properties of these rocks. And I'll give you a couple of examples. So in this example, we're drilling a well, maybe for oil and gas or maybe for geothermal energy into a homogeneous unit. And you might imagine the engineering involved would be quite different if this is actually a very heterogeneous sort of layered package. The same is true of a repository for, say, radioactive waste. Is it homogeneous or is it layered? And we can see at the micron scale, these things are actually really quite complicated. So that basically sets the scene for my PhD. It was basically trying to untangle the heterogeneity and relate that back to geological processes. So really, I guess the main thing to keep in mind from this point onwards, when we're talking about process, these rocks are around 300 million years old. We're thinking about processes that were operating sort of in a marine environment, in sort of basically chemical reactions going on close to seabed and in the very shallow, sort of really soft, squishy mud part of the sort of sedimentary column. So how do we untangle this complexity? So we're first already kind of exploring one approach, which is basically looking at textural changes and basically comparing that to modern analogues. We can also use a variety of geochemical techniques. So we can use wet chemistry to basically dissolve out the pyrite fraction in these rocks. So pyrite is particularly widespread and is so important to the heterogeneity story because basically it precipitates under conditions which lack oxygen, so anaerobic conditions. And in a very general sense, we know that mudstone heterogeneity is essentially driven by changes in the amount of oxygen in the environment during deposition. So pyrite is a really important part of that story. So we can quantify it, basically to try and quantify the degree of sort of limitation of oxygen during deposition. So we can also look at bulk geochemistry. So I've already touched on the fact that there's a lot sort of these things can be mined for their metals. So there's a wide suite of metals present in the Bowline Shale, typically fairly low concentrations. But for the purpose of this talk and really the highlight of my PhD, we're going to focus on two metals we term redox sensitive in the marine environment. So that's vanadium and nickel. And we've already touched on the importance of trying to understand why there's so much vanadium in the Bowline Shale. And I guess the main conclusion from my PhD really was about defining a new environment at which these rocks were being deposited. So it's a mode that we've termed redox oscillation. And that, in simple terms, when we plot something like vanadium, the concentration of vanadium against nickel in these rocks, typically a black shale would sort of, those points should sit on a sort of a fairly even one-to-one line. In the Bowline Shale, they don't. They're all over the place. We've seen this relationship in oils. We've never seen this in the bulk rock before. And this is really telling us something quite unique about the Bowline Shale potentially, and something that's very interesting. So what we believe is going on is this is a competitive relationship. So this is basically a function of the amount of oxygen in the environment and also the pH. It's basically these metals are competing for a fixation site in an organic molecule, a porphyrin compound, which is essentially sourced from chlorophyll. And this competitive relationship is essentially dependent on the redox potential, so basically the amount of oxygen in the environment and the pH conditions. We've essentially used those findings. I'm not going to go into too much detail, but we can start now to predict the heterogeneity in the Bowline Shale, both temporally and spatially. And we're also developing ways in which we can recognise certain layers with much greater ease. But I guess to summarise what the environment would look like, and to come back to this heterogeneity, a good place to start might be, for a modern analogue, something like the Black Sea. So the Black Sea is a strongly restricted basin. It's a well-stratified water column, and basically what that means is we have a well-oxygenated, habitable environment in the upper part of the water column, but actually below about 200 metres you won't find any aerobic life. So there's no fish, basically. So it's a very inhospitable environment because it's anoxic. So it's anoxic and also it's sulfidic. So you'll actually get crystals of pyrite precipitating in the Black Sea. So this is probably a partial analogue to what we were seeing in some of these ancient black shale settings. But the heterogeneity is essentially related to fluctuation between an environment like that and something that was much more habitable and well oxygenated. The story with the vanadium and nickel is basically showing that there was actually some other kind of state where we probably don't have a modern analogue. So some kind of oscillatory state is ultimately likely related to the evolution of phytoplankton. So it's probably the type of plankton that were actually existing millions of years ago and we just don't have in the present day. And it's essentially driving the the chemistry, the chemical reactions in a very different direction. So just for the last couple of minutes, I'm going to now kind of get onto the topic of machine reading. So still keeping with the theme of heterogeneity, and we're thinking about ways of trying to scale up these observations and these findings to try and make some more sort of generalized geological interpretations. So what we're interested in is we're interested in occurrences where people have described these textures and reported them in the literature. So essentially we're using a machine reading technique of the published literature. So that's essentially through an agreement with all of the main publishing houses to essentially access all of that published literature and conduct some analysis of that material in order to essentially extract a proxy for mudstone heterogeneity through geological time. So I'll just kind of go through how this works, but basically we've analysed just over 11 million documents using a natural language processing workflow using a library machine reading system called Geodeep Dive. We've basically developed an algorithm which links different descriptive terms for pyrite and stratigraphic names, things like the Bowline Shale. So here we have a sentence which was included as part of this analysis. So pyrite framboids, aggregates of some submicron pyrite crystals, are relatively common in Horn River group shales. So natural language processing basically tags a series of parts of speech and linguistic dependencies and highlights there's essentially a relationship or a tuple between the phrase pyrite framboids and Horn River group. And we can repeat that process essentially for every sentence in every document in that library. And by doing so, we can start to reconstruct really large-scale geological records through time. So on the x-axis here, we have time in million years. So we're going all the way back to over, around 3.5 billion years. This is a really, really long time. Complex life had evolved, was starting to evolve around here, around 550 million years. So I'm not going to go into too much detail about the interpretation of this plot, but I guess the key thing is there's some spikes here, which basically are saying that we're looking at more widespread deposition of black shale, pyrite-bearing sedimentary rocks in the geological record. And some of these aren't surprises in that these tie in quite nicely with known mass extinction events, where we know that basically there's a really catastrophic collapse in the marine biosphere associated with expansion of anoxic conditions. And so I guess that's a whistle-stop tour through some kind of recent research on black shale. So I'd just like to conclude and hopefully I've highlighted that black shales are really important for many reasons, not just shale gas. So if you think about metals and other uses, things like in carbon capture and storage. We've defined a new redox oscillation mode, and we're really kind of at the early stages of appreciating how important or perhaps not this process may be. And I guess this will really we'll have to see with sort of more research testing how widespread this mechanism was. And I've also touched on the use of some big data techniques, which is starting to, I guess, modernise some aspects of geology. And on that note, thank you for listening.
Fantastic. So, some questions. We've got time for 2 or 3 quick questions from the audience. Anybody wants to run on the line? Okay.
Do you want to say something about the distribution of Bowline shale?
Yeah. So quite reasonably localised to particular parts of the UK, but there are time equivalent units all around the world. So a very famous shale gas target called the Barnett Shale is basically a time equivalent to the Bowline Shale. The problem with, in a way, there's a lot of jargon and nomenclature in the world of geology, but in terms of time equivalent units, reasonably widespread. But obviously it's a function of plate tectonics, ultimately. So, 330 million years ago, the world looked very different. Plate tectonic configuration was very different, and that ultimately drives where the present day distribution is.
Another question?
Is this stuff one of the oil? Is it what would be oil in the future? Or in the right conditions?
Yes, in a way, yeah. So the organic, so these are organic rich materials, and shales, if they're buried enough, the organic structures break down under temperature and pressure, basically break up to produce oil and gas, and then the oil and gas will basically either sit within really small tight pores within the rock, which is essentially what a shale gas is. It's actually fracturing a shale and recovering gas out of the pore network, or it migrates, so it actually moves through the geological layers into a more porous rock. And that's kind of, when you think of it like a cartoon oil well with oil actually flowing under pressure out at the surface, that's a conventional oil target, where basically the oil is sitting in a very porous rock, basically like a sponge.
You say that these contains nickel and vanadium. Do we or should we be mining this?
Yeah, it's a good question. Yeah. So it's probably not an appropriate target for mining, certainly not in the UK. I mean, these things tend to be high tonnage, low grade deposits, so really not preferable, certainly in the UK. But where we're going with this is thinking about, okay, that the environment is sort of the entry point for the metals, but actually during burial, there's all kinds of reactions that go on which can mobilize those metals and move them in fluids and basically concentrate them locally in other rocks. And in fact, we see that relationship with the Bowline Shale. So a lot of historic lead zinc mining in Yorkshire, the metals or the sulfur comes from the Bowline Shale. So during burial, those materials were basically expelled and migrated in fluids and then precipitated along fractures in the limestone that's present in, say, Yorkshire. So we're looking at similar potential in terms of vanadium and nickel.
I think we've run out of time for questions. So we're going to shamelessly get a photograph for the Doctoral College. So there is a certificate, and if you just smile at Alex, there is a certificate there. You can see it's got your name on it. There is seriously.